Okay, folks, I think we might as well go ahead and get started here. It's my pleasure to introduce today's speaker, Dr. Raphael Stern. Raphael got his doctorate from the University of Illinois at Champaign-Urbana in 2018, if I remember right. I did some post-work at the Technical Institute of Munich, okay, and then started a appointment as an assistant professor here, all right, in August of 2019. One of the things that Raphael is interested in is the kind of the elephant in the room in the transportation business, which is what are automated vehicles going to do to everything that we've been doing over the past 50 years. As an aside, I was working on a topic where I was trying to predict what would happen to frequency of rear-end crashes on freeways if we had automated vehicles there. Unfortunately, finding out how automated vehicles worked was a well-kept secret, okay, by the automobile companies. But one of the things Raphael had been working on was characterizing how these vehicles behave using field data. And his paper turned out to be just exactly what I needed here. So with that, I'll turn it over to Raphael. Thank you very much.
Thank you, Gary, for the introduction. I am going to, thank you. And thank you for really great to see a lot of faculty. I know there's a bunch of people online and in the room and a lot of students, especially undergraduate students. It's really nice to see you. Last time Gary introduced me to give a talk was 6.5 years ago in March of 2018. And what I want to do today is basically pick up where I left off. So there's going to be a tiny bit of overlap at the end for those of you who were in the room at that time. And I want to talk about a lot of that stuff, that sort of where I've gone from there in terms of the work that Gary was just mentioning. So before I get started on the topic of today's talk, I want to sort of place my work generally in sort of a broader context. I'm going to talk about one of the projects that I've been working on here at the University of Minnesota, but the work that I do all kind of revolves around this central question of how do you use data to inform the control and management of transportation systems. There's a whole bunch of new data sources coming online, and we can use these to better manage the transportation infrastructure that we have. A large part of sort of my philosophy about this is we have spent decades and decades and billions of dollars building infrastructure, and saying something like automated vehicles is going to totally change the infrastructure that we need is unfortunate, because I just don't think it's going to happen if it requires us to rebuild all of our roads and bridges and all the infrastructure we've built. So a large part of the work that I do sort of looks at what do we have, how do we take data to improve how we're managing what we have, what maybe smaller updates do we need to make. That includes work with vulnerable road users like bicyclists, pedestrians. During COVID, I got really interested in sort of mobility data as a whole and how that influences viral spread modeling. A lot of stuff with deer, actually not that much stuff with deer, but people seem to be interested in it. And what I want to talk about today is sort of what might happen when we have automated vehicles. And I think we are both closer and further from having automated vehicles than you may think we are. I'll talk about what I mean with that. So automated vehicles, they've had a lot of hype over the last several decades, more so in the last maybe decade or so. And there's a lot of different aspects how automated vehicles might totally change the way we think about transportation. I want to talk about a couple of these, and this is not what I want to talk about today, but I think it's important to at least set the stage and understand how automated vehicles have the potential to really transform the way we think about transportation and mobility. The first question that's sort of out there is what will happen to vehicle miles traveled? VMT is a commonly used metric that traffic engineers use to decide how to allocate resources in terms of road repair, road improvement, et cetera. And there's different scenarios that could play out depending on how automated vehicles sort of are introduced. On the one hand, there's a lot of work. We've seen some Warren lectures here present on work on pooled automated shuttles. And so if people, I commuted in this morning, I came by bike, but if I had driven, I'm sure there were other people coming up from South Minneapolis. And we could have probably at a similar time, we could have potentially pooled a ride. And if we didn't have to worry about a driver, et cetera, we could have a shared shuttle pick us up, drop us both off here, potentially taking 2 trips, reduce those to 1. That's a reduction of vehicle miles traveled. The other way to think about an automated vehicle is it's effectively a chauffeur. And so now all of a sudden, if at 11 o'clock at night, you want to go get some food, you can just get in that automated vehicle and drive and get that, not worry about being sleepy. Actually, why get in the car? Just have the car do the work. Just have the car drive, come back, and now you might even have like ghost trips that occur without a human in the car. And you could potentially see a big increase. You effectively reduce the cost to travel, you've reduced the cost of the time, you could see a big increase in vehicle mile traveled. Similar, I mean, automated vehicles have the potential to change how we think about land use. University of Minnesota is an urban campus. Real estate here is not super expensive, but reasonably expensive. If you look at a satellite photo of the University of Minnesota campus, you will notice there are huge parts of our campus that are surface parking. They're used to park cars. If we have automated vehicles, potentially we could reduce some of that because those cars might not need to park. They might be able to drop you off at work or drop you off at class and then go pick up someone else. And we could use that to build, I don't know, more dorms, more graduate student housing, right? The other scenario that could play out is sort of think back to that chauffeur example. We've gotten used to work from home. Why not work from car, right? What's stopping me from living up in Duluth, commuting down in the morning, spending the first 2 hours on Zoom meetings because the car is driving me, few meetings in person during the day, drive back in the evening. All of a sudden, we might see sort of this fueling massive urban sprawl. There's a third area where automated vehicles have the potential to make real impact, real change, and that is safety. And again, there's kind of different scenarios. If you look at the automated vehicles we have, there's suggestions that they might not actually be as reliable as human drivers right now, but there's also potential in the long run for them to be much more reliable because humans text, humans drink and drive, automated vehicles don't do any of that. Okay, so these are all the things I'm not going to talk about. But I think they're important things to keep in mind because I think they really set the stage for the entire conversation about how vehicle automation can impact sort of how we think about transportation. What I want to think about is how will increased vehicle autonomy impact traffic flow? This is the topic that I'm really passionate about. And back to sort of that central question that sort of guides a lot of what I've done here. Okay, so things might be different. What does that mean for how we manage the infrastructure? And what I'm really interested in, I love traffic jams. I hate being in them. I love them. What I'm really interested in is something called phantom traffic jams. These are real jams. These are real traffic jams that occur for no good reason or no apparent reason is probably the better way to put that. So we see them in the wild. I'll say at the top here. This is one, I believe, in North Florida or South Georgia. And you see a really like nice jam that propagates. There's no crash. There's no construction. There's no police officer causing people to suddenly slow down. There's just a traffic jam for no good reason. Right? For a long time, it's kind of a nice story. For a long time, there was a big debate in the traffic engineering community. Are these real? Are they caused by some sort of bottleneck that we're just not seeing? Is it that there's glare on the road? Is it or are these sort of just an artifact of how traffic flows? In 2008, a group of physicists, actually, I love that it was physicists who said, well, we'll do what physicists do. We're going to do an experiment. We're going to test this. So a group of physicists in Japan got a bunch of cars, set up a big track in a circle. They start all the cars at the same speed, same spacing, so uniform flow. And no matter how many times they run the experiment, all the cars start driving. They're driving at the same speed, same spacing, and I don't know, within a minute or so, there's a traffic jam that arises. And I know that happens every time because I've done this about 20 times myself. And every single time you see a traffic jam. So what's really going on here? What are these? Phantom jams are a result of something that we call string instability. Now, you may have heard of a whole bunch of different notions of stability. String instability is a very specific notion that refers to what happens to perturbations in the flow. So imagine a string or a platoon of vehicles, a group of vehicles, they're driving along, they're at what we call equilibrium. They're happy. They're happy with the speed that they're driving at. So every vehicle is driving at the same speed, the same spacing, and they're not accelerating. So they're all driving along happily. And now imagine the first vehicle in that platoon hits the brakes. So asymptotic stability might refer to what happens to that vehicle over time, but string stability refers to what happens to that perturbation. The vehicle behind it is going to have to hit the brakes. And the question of string stability is, does that perturbation amplify to subsequent vehicles? Or, in the case of string unstable traffic, or does that perturbation dissipate to subsequent vehicles in the case of string stable traffic? And this is the key to whether or not you're going to have those instabilities or those phantom jams arise, is this string instability. Okay, these things are, I want to say, they're phantom jams, but they're very, very real. So here's some relatively recent data off this is trajectory level data. So we're seeing each vehicle, it's over like 4 miles of road. So you just see like, there's just way too many vehicles. 4 different lanes of traffic outside of Nashville, Tennessee, where they have a sort of an array of cameras. Sort of like what we had in the MTO on I-94, but for 4 miles. And you see these things sort of arise out of the blue. they grow, some of them split. They have a life of their own. Some of them merge. You can see some of them merge. They have really interesting sort of dynamics of their own. It's sort of like, I don't know, looking at zebra stripes or something and trying to make sense of it. What's going on here? Okay, so this is what traffic looks like in the wild. When I spoke here, I think it was 6.5 years ago, I had a result that I was super proud to present. And I want to show it now because I think it kind of sets the stage for a lot of what I've done since then. And the question was, okay, think back to that ring road experiment that I showed you from Japan, 22 cars on a circular ring, they're all driving, chaos ensues. What happens if we start to have a small number of those vehicles where we can control how they drive? That's the central question here. Imagine you can make some of those vehicles drive better. I'm just going to show the video here that kind of shows what's going on. So this is the exact same setup, 22 cars on a ring, the vehicle with the arrow on top of it, it's autonomous capable. It's currently being driven by a human driver. You see the speeds down here, that vehicle is highlighted in black, the other vehicles are sort of all shown in gray. And relatively quickly, this is sped up a little bit, within about 1.5 minutes, big stop and go waves emerge. It's going to happen. Now at this point, we've activated the autonomous controller on that car. That car drives differently. The other cars actually, the drivers in the other cars have no idea what's going on. But that one car driving better forces everyone else to drive better, which is kind of cool, right? Think about what you could do if you drove better. Okay, so here's the results. At the top, we have what's called a space-time diagram. Traffic engineers love these. Each of those lines is just sort of the position of each car over time. The steeper the slope, the faster they're going. When you see something like that, that's a wave, that's a slowdown. And you can see really nicely at the beginning, we have these stop and go waves, these phantom jams that arise. There's no bottleneck there, right? Those are just straight up phantom jams. But relatively quickly, we activate the controller and we see smooth traffic. We measured data off each vehicle. We saw a huge reduction in fuel consumption, a slight increase in throughput, because instead of slowing and speeding up, we see maybe a 15% or so increase in throughput. Okay, so that was the result that I was super excited to share. The question is, how realistic is this? And that's what I want to spend the rest of today talking about, is can we actually do this? And there's an important thing that we need to sort of all be on the same pages, and that is that not all automated vehicles are the same. There's different levels of automation, and each level of automation means a different thing. So the Society of Automotive Engineers defines 5 different levels of automation. I guess 6, because there's level 0, no automation. That's what I personally drive. So in no automation, who's steering and accelerating? That's the human driver. Monitoring the environment, that's the human driver. If something goes wrong, the human driver needs to slam on the brakes or veer to avoid a crash. There's no robot on the car. But as you go to lower levels of automation, level 1, driver assistance, these are features that you might be familiar with. We start to take some of those driving tasks, take them from the vehicle and hand them off, take them from the human and hand them off to the vehicle. And as we go up to higher levels of automation, level 2 partial automation, conditional automation, high automation, and finally up to level 4, 5 full automation, what we're seeing is more and more of these driving tasks in more and more driving contexts. So some of these might only be on pre-mapped freeways, whereas being able to do this in all driving domains are handed over to from the driver to the car. And so those results that I showed, they might be feasible if we're somewhere here, right? 3, 4, maybe 5. The reality is, what we've got, at least for the foreseeable future, I mean, I feel like a few months ago, every week, another autonomous car company went bankrupt. There's just still a lot to be done at these higher levels of automation. What we have for the foreseeable future is these lower levels of automation. So I want to start there. One feature that I'm particularly interested in, because it does exactly what we want it to do in terms of sort of controlling the flow of traffic, is it changes the way that individual vehicle drives, and that's adaptive cruise control. Remember back to that video on the ring, what we really saw there was if you change the way a small number of vehicles drive, you change the way the whole flow behaves. You change the emergent properties of the dynamics of that whole traffic flow. And adaptive cruise control used to be a luxury feature, but now most new cars have it. Many new cars have it. I dare say most new cars have it. What it is it's like a traditional cruise control, but it uses a radar to also maintain a safe safe spacing. So you want to drive at 65 miles per hour, you set your adaptive cruise control at 65. It cruises along at 65 until a car driving slower appears in front of you. It'll slow down to avoid a collision. And then as soon as that car, I don't know, changes lanes, speeds up, your adaptive cruise controller will speed back up. That is exactly what we want, right? We want to be able to control something like that. Now, if you look at the literature and you ask, okay, but are these things string stable? There's literature going back to from before I was born, right around when I was born, early 90s, that says a resounding yes. Adaptive cruise controllers can be string stable, end of story. But it turns out that if you actually look at the way these systems work, this is in theory, but in practice, there's a slightly different story. And that's what I want to investigate a little bit right now. This is some work that I did early on while I was here. So in order to analyze what these systems look like with respect to string stability, we first need to be able to characterize the string stability of a driving system. What we need for that is we need to be able to represent that system somehow. What I'm going to do is I'm going to use something called car following models or microscopic models. These are ordinary differential equations that describe the acceleration of a vehicle as a function of the spacing with respect to the vehicle in front of it, the speed that the vehicle is traveling at, and whether or not it's catching up to the vehicle in front, or how quickly it's catching up or falling behind the vehicle in front, the relative speed between the two vehicles. Common assumption made, I don't know, back to the mid-50s or so, with some of the first car following models out of GM that describe the dynamics of a vehicle as an ordinary differential equation with this state. Okay, so if we have one of these, the question of string stability is a platoon of these vehicles or a group of these vehicles driving at equilibrium. What happens to small perturbations? So we have that same equilibrium we had before, zero acceleration, same speed, same spacing. And we introduce a small perturbation. And the question is, what happens to that perturbation through the dynamics? So we can couple these ODEs and watch what happens to that perturbation. The key result that I want to get to is that it turns out it's actually, if you know the partial derivatives of the car following model or of that microscopic, that ordinary differential equation, you can very easily characterize whether or not that vehicle is string stable. And so you come up with this lambda 2. Happy to go into details on what that is. It's the curvature of the Bode plot. But I think the important thing is you come up with this lambda 2. The nice thing is it depends only on the partial derivatives of the model. So if you know what your model is, it's calculus, but you can easily derive what those partial derivatives are, and you can easily get your lambda 2. If lambda 2 is less than 0, we're going to see dissipating behavior. That's a string stable vehicle. It's going to tend to sort of smooth traffic waves. If lambda 2 is greater than 0, it's string unstable. It's going to tend to amplify those waves. Okay, so now we have a model, and we have a tool to analyze that model. What we need is data, and I think this is what Dr. Davis was getting at before, is we need to collect data. And so the goal here is to observe what these vehicles behave like. Now, you might say, hey, car companies built that. They know how it behaves. So two things. First of all, they're never going to tell me. I tried. They won't tell me. Second of all, and perhaps more importantly, they know how they think they built it. But they have some relatively straightforward controller. And for anyone who sort of knows something about controls, it's a PID controller that runs on that car and then runs through this highly nonlinear system, which includes a gearbox, an engine, or transmission, an engine, all sorts of different components. Add to that all sorts of different, external variables, such as wind speed, et cetera. Even things like air temperature, humidity affect how that engine is going to behave. So you'd need a, 1,000-dimensional model to accurately be able to assess this. And you need the knowledge from the car company, which, again, they're not going to give you. So what I want to do is I want to think of this more as a system identification problem. Sort of think of this from the control theory standpoint, system identification. I want to see, I give this an input. This car in front of it brakes. How does this respond? I want to build this as a black box in the form of those car following models, because I just spent, 3 minutes telling you how I can nicely analyze those car following models for string stability. So the model I'm going to use is really pretty straightforward. And I'll talk in a little more detail on sort of variants of this and variations that we've developed here. But the basic model that I want to use is an optimal velocity, relative velocity model. There's two terms to it. This first term is, who here learned the 2-second rule in driver's ed? This is follow the tau second rule. Stay tau seconds behind the vehicle in front of you. So if you're going faster, increase that spacing. The second term is sort of a relaxation toward the leader velocity. If the vehicle in front of you starts to brake, you don't want to overshoot. You want to be slightly more reactive. Okay. And so the experimental setup here is really pretty simple. get two cars, make sure one of them has adaptive cruise control, get high accuracy GPS sensors, mount those on each car, drive, have the vehicle in front brake, the vehicle in back follows with ACC on, record the signal for each of those. You get the spacing, you get the speed of each, you get the relative speed, and you're in business. Did this with a whole bunch of different cars, just to give you a sense of what some of this looks like. So here's that lead vehicle making relatively small oscillations, and a following vehicle making bigger oscillations behind. You might be able to tell where the story is going. I tested it originally on 7 vehicles. I've since tested it on a bunch more over the last couple of years. More on that in just a second. But I wanted to get a sense of small cars, large cars, hybrid cars, internal combustion engine cars. What's the range of behavior we might see here? Okay, so in summary, we've got 2-vehicle experiment that gives us data. We take that data, put it through a relatively straightforward sort of optimization routine to find the best fit model parameters that make that model that I showed you, remember that 2-second rule or that tau second rule model, look like each of those vehicles, each of those 7 vehicles. We get values. We test them. Most of these cars, if you have one of these systems, you'll know that there's generally like a close following spacing and there's different user settings. And so some cars have 2 settings. I've seen some cars have 7 settings. I don't know who needs that much specificity in terms of how far they follow, but some cars offer that. We tested at the minimum and the maximum, and we get our model parameter values. We get a mean absolute error. This is a headway mean absolute error. So if the vehicle is trying to follow 2 seconds behind, we're off by 1/10 of a second. And we can look at what sort of in blue, we have the simulated trajectory using our model, speed, spacing, headway. Headway is the time gap. And in orange, we have the real data. And it matches pretty well. This very simple model is actually really able to capture most of those dynamics, or a lot of those dynamics. We can do this for all the 7 vehicles, both the minimum and the maximum setting. There's 2 things I want to point out. The first thing is we're seeing on the order of a 1/10 to a 20th of a second error in headway, in time gap between the model and the data. I think that's pretty good. And the second thing is we can look at those lambda2 values and all of them are greater than 0. So what this means from a traffic flow perspective is all of these are going to amplify traffic waves. Okay. I did start like 10 minutes ago, 12 minutes ago by saying humans do this. So I think the next logical question is, okay, but are they worse than humans? How do they compare to humans? So I had a student, Mingfeng Sheng, who's now at the University of Arizona, recently graduated, who spent a large part of his work looking at exactly this question. We have these models. We spent a lot of time building models for these. We have a lot of data, but how do they compare to human drivers? What I want to sort of share is just one of these results here that I think nicely illustrates how these vehicles might differ from or relate to or compared to human drivers. So I want to test basically 2 different scenarios. One of these commercially available internal combustion engine ACC vehicles. If you know anything about car models, you might be able to guess what this car was. This is one of the models that we spent a lot of time tuning, building, et cetera. And a theoretical vehicle that's going to drive very similar to that vehicle that I showed at the beginning. So the result for this, we ought to know, because I just showed you the video. It ought to be, I don't know, 10 to 20% increase in throughput, right? But we're going to look at a merge bottleneck, and I'm going to point out that it's hard to see, but that's kilometers per hour, is not miles per hour, 90 kilometers per hour. That's an important detail. We're going to look at a merge bottleneck, common bottleneck that you might see, and we're going to look at different market penetration rates or different percentages of traffic being both commercially available ACC vehicles as opposed to 100% human-driven, right? We're going to reduce from 100% human-driven, 90%, 80%, et cetera, as well as theoretical AVs. Okay, before I show the results, I need to do a quick primer on some basic traffic flow theory. If you're in fluid mechanics, you might see some overlap here in terms of how we think about this. So let's go back to 1935, Bruce Greenshields. There he is, professor at the University of the Ohio State University. Apologies. And he had this idea that the speed of traffic ought to depend on the number of vehicles on the road, or the density of vehicles on the road. He had a hunch, I would say. He went out and collected data. This is him collecting data here. He had 2 cameras set up that took pictures at when vehicles passed so that he could see what the speed of the vehicle was. And then he was able to look at, also count the number of vehicles and look at the density. This was 1935. Automobiles were pretty rare. So he got a whole bunch of data on the upper left-hand side there at low densities in terms of vehicles per mile, but relatively high speed. He got one data point all the way down here at a high density, low speed. He did what any good engineer does, is he drew a line through it. This is called the Green-Shields diagram. And it's this sort of linear decreasing relationship between spacing and speed. Okay, one of the important relationships in traffic flow is that if you know the speed and you know the spacing, you also know the flow. So speed is miles per hour, spacing, or rather density, is vehicles per mile. And if you know miles per hour and vehicles per mile, and you do the dimensional analysis, you'll see that we can get vehicles per hour. And ultimately, as traffic engineers, that is a metric that we care about a lot, because that is how many people we can get across our infrastructure in any given hour of the day. So this linear relationship, you multiply that through by speed again, you're going to get a quadratic low density relationship. In traffic engineering, we call this our fundamental diagram. It's that important to us. I was at a conference where there were a lot of applied mathematicians, and one of them was like, my colleagues in applied math think it's so cool that in transportation engineering, you have something that is so important, you call it your fundamental diagram. So, and everyone knows this is the fundamental diagram. Okay, so if you look at data though, so this is this sort of, if you assume that linear relationship between speed and spacing, we've got two different parts of this and two different important components, a couple different important numbers. On the left-hand side, so right here in the middle, we've got this critical density. That is the density at which congestion starts to show up. On the left-hand side, we have free flow. On the right-hand side, we have congestion. At the top, the maximum sustained flow, that's our capacity. Obviously, if you are a transportation engineer, you want two things. You want that capacity to be high, and you want this critical density, this breakdown point, to be as far to the right as possible. Because that means that you can sustain traffic at high densities that's flowing smoothly, and you can get a lot of vehicles across your infrastructure. If you look at data, it turns out this, while it's mathematically quite nice, this parabolic fundamental diagram or flow density relationship isn't that realistic. And something that's triangular, generally lopsided triangular, is more consistent with the data. But fundamentals are the same. Shouldn't use the word fundamentals. The concepts are the same. We have that free flow and congestion. Okay, so now I can show you the results. First, let's look at the fully automated vehicle. These results should be the least surprising results you will see in a talk here. It turns out that when we put in more and more fully automated vehicles, what we see is two things. First of all, it's kind of hard to tell. This is pretty characteristic scatter over here. But generally, that breakdown speed is moving to the right to a higher density. I don't know, maybe 20, 30% more vehicles per mile possible if you get really well-built automated vehicles. And generally, that maximum sustained flow is moving up. It's not moving up a lot. If you add in connectivity, that's something I'm not talking about today. That's where you start to see these 2, 3x capacity. But if you're not relying on connectivity, you're not going to get more than maybe 15 or 20% more. But you can potentially get 15 or 20% more just by sort of smoothing out that flow. Okay, so that is fully automated vehicles. With ACC, I want to use some of those models that my student built to look at what that happens. So here is our fully human 0% ACC. It's going to show sort of these fundamental diagrams for subsequently sort of more and more ACC traffic. What you see is two things. You see kind of a collapse of that fundamental diagram. You see that critical density, that breakdown point, moves to the left, and you see that capacity comes down. So potentially these things are overreactive. We saw that a few minutes ago. They're conservative. They leave bigger spacing, and they reduce the capacity of the road. Potentially up to, I don't know, 30, 35% reduction in capacity. So if you're a traffic engineer and you have a 6-lane freeway, if everyone turns on ACC, you may have a 5-lane freeway. That might matter, right? There's a little bit of good news for those of you who drive electric vehicles. I've recently started collecting some data on electric vehicles, and not to get too far into the details of sort of the powertrains of electric vehicles, they have full torque at low speeds, which means it's what makes electric vehicles so much fun to drive, because you hit the gas and you go. It also means that a lot of that nonlinearity that I was talking about between that string stable controller that somebody designed, I don't know, in the early 90s or something, and what happens when the tires literally sort of go across the pavement, it's a lot simpler. And so if you look at some of this data, I've been collecting data for a couple of electric vehicles, electric ACC vehicles. On the left-hand side, this is sort of lead vehicle in blue, following vehicle in orange. That's the data that I already showed you for a conventional internal combustion engine vehicle. If you look at an electric vehicle, same style type of braking event, almost exact same braking event. Actually, more extreme braking event in this case, starting same speed roughly. You see a little, you don't see that overshoot. And you see actually a little bit of maybe what I'll call jam absorption. These vehicles have very different braking and acceleration behavior. So if you look at the spacing versus acceleration, you see lopsided behavior. The simpler models that are out there just don't capture that. And while you might say, oh, these are details, I'm not sure if these really matter. I think they are relevant because we're exactly trying to model this like very specific acceleration and braking behavior. So my student and I built a new model that sort of incorporates some of that asymmetry. There's some nice analysis that can be done on this to show under what conditions this is string stable. It's now a discontinuous system, so it's a lot, or a hybrid system. It's a lot more complicated to analyze, but it captures the dynamics of those vehicles a lot better. If you start to look at sort of like simulations of groups of these vehicles driving, you can see that. So that lead vehicle is from actual data, lead vehicle data, braking, an electric vehicle following with data, braking, and then simulated. And you see that there might be sort of a less congested future as we see more automated or more electric, partially automated vehicles. Okay, so that's the first part, what I want to talk about. The second part of what I want to talk about is the sort of that second question that I brought up. And that is, okay, cool. So we're seeing potentially very different traffic flow. Changing the dynamics of traffic, of individual constituents of the flow, changes the flow. If I'm a traffic engineer who's managing a piece of infrastructure, what do I do with this information? So I want to sort of introduce a vision for how we might be able to manage traffic in the future that looks at who's showed up to drive today, what percentage of vehicles are automated, what are their specific characteristics, what does that mean? So that requires us to identify who's there. What does that mean in terms of what that aggregate flow is what are the emergent properties of that aggregate flow? What are those flow dynamics? And then how do we take the existing control and update it? Hopefully the answer is not like everyone needs to buy a certain car or everyone needs to have this device installed in their car, but something like we can take the ramp meter and change it a little bit to be responsive to the current market penetration rate of the current fraction of vehicles that are driving differently. Let's say they're ACC, driving maybe a little more conservatively. So I want to step through sort of work that I've done here on each of these. I'll go relatively fast on some of them because there's just sort of key results that I want to share. And then I'm going to go into a little more details on some of them because I think there's some nice methodological work that can be done there. Okay. The first thing is the identification of vehicle. What we really want to do is we want to watch a vehicle drive, and we want to be able to sort of identify almost like a unique driving signature. What does this vehicle behavior? What is its dynamical response to a certain stimulus or to a certain input? Now, of course, we can't control what that input is, right? We're just watching traffic. So we have to hope that it has to brake at some point and that we see what it's braking in response to, because otherwise, if it's just driving at 60 miles an hour without any change, we're not going to be able to actually observe that. Okay. So one of the technologies that's become pretty pervasive is cameras. So we have actually relatively good data of vehicles driving and vehicles following other vehicles. You saw, I think Professor Choi talked about this in the spring, about like what you can do with this type of vehicle sort of video data. So my student Tianyi Li and I came up with basically a pipeline for looking at vehicles, leader vehicle, following vehicle. How is that vehicle following? And then taking that, putting it through a neural net to identify what vehicle it is. With the 15 minutes or 10 minutes I have left, I'm not going to go into all of the painstaking details of how this works, but the results are quite nice. In about 85% of the cases, we can look at a car, look at it driving a little later on, and re-identify that same vehicle based on the way it's braking. This only works, so we can do it with a very small set of vehicles right now. We can't do it in the general public, right? So we can do it with, if we know there's 5 different cars driving, we can identify 1, 2, 3, 4, 5. I can't re-identify that in the general public. That is a much harder problem. But this is a step in the right direction, right? We are starting to get to the point where we can look at a vehicle, see it drive, and then re-identify it. Okay, so now if we know who's there, it's a little bit of a jump, but just bear with me here, please. If we know who's there, the next question is, how do they influence the entire properties of that flow? And that's what I want to talk about next. So how do we basically know the vehicles who showed up to drive today to get the flow dynamics? What we've been talking about so far is microscopic or vehicle level dynamics. When we talked about the fundamental diagram, we were talking about macroscopic or flow level dynamics. So we need to be able to go from those microscopic vehicle level dynamics. We know 20% of vehicles are ACC, 80% are human drivers. What is that fundamental diagram going to look like? Because that is what we're ultimately going to use for control. Remember, what do we want as traffic engineers? We want to be close to capacity or close to that breakdown point without going over that breakdown point. So we need to know where that breakdown point is. Okay, so the basics behind this idea is in an uncongested flow, we're going to assume that vehicles are traveling at free flow, and that's pretty consistent with the data. I don't know if you recall from that fundamental diagram that I showed earlier, but up sort of in the clustered area, those points were pretty, or sorry, the green shields plot that I showed earlier, those points were close together. In congestion, this is where things get a little more interesting. We're going to assume one of those microscopic car following models. So we're starting with the vehicle level. If they are at equilibrium, which these fundamental diagrams are equilibrium curves, we have a speed spacing relationship. And so we can derive, if we know what the car following model is, we can derive what that speed spacing relationship is. It's algebra. It's not fun for some of the more complicated models, but it's generally doable. If we know spacing, the reciprocal of spacing is density. So now we know density. If we know speed and density, we know flow. So this is a pretty standard exercise. Students in my more advanced classes have done this, I think. Where it gets interesting is when you have a whole bunch of different vehicles that drive differently. So you have different classes of vehicles. We can follow that same approach, but now we have to sort of come up with an average equivalent spacing. And so we can do that. We come up with an average equivalent spacing based on this gamma, which is the market penetration rate, or the fraction of vehicles that have each class. And you can sort of do this for 2 cases or for n cases. And you can come up with a flow density relationship that depends both on a flow relationship that depends both on the current average density as well as who's there, what the market penetration rate is of automated vehicles, ACC vehicles, et cetera. Okay, so that same fundamental diagram that we had before, remember that triangular fundamental diagram that I showed, it now has a 3rd dimension. So we still have density. Oh, I'm not allowed to go there. We still have density and flow on the horizontal and vertical axis, but we also have a 3rd axis, which is percentage of vehicles that are automated. And what you see, perhaps unsurprising if you've seen the previous results, is that capacity starts to taper off at higher and higher market penetration rates. And if you were to look at it, you'd also see that where it is, if you project this line here into the density market penetration rate plane, you'd see it start to go down at higher market penetration rates. That's that traffic congestion setting in earlier and earlier. Okay, so now we have the first part, we can identify who showed up. We have the second part, we know based on who showed up, what the traffic's going to look like. The last thing I need to show you is that third part. How do we now change the way we control or manage our infrastructure? And as an example, you could do this with any sort of infrastructure control technique where you're looking at density and changing something in response. As an example, I'm going to show you ramp metering because here in the Twin Cities, we are a leader in ramp metering, at least in the United States. All of the results that say ramp metering works come from a single experiment that was done, or not, that's not quite true. Many of the results come from an experiment that was done here in the Twin Cities, I think in the early 2000s, when they shut off all the ramp meters because people were fed up with them. And it turns out congestion increased quite a bit during the 2 weeks that they shut off the ramp meters. Okay, so how do ramp meters work? The simple idea is it's a traffic light or a stoplight at the entrance to the ramp, and you are controlling the flow rate. You cannot control the flow rate on the main line. You can control how much, sort of it's like a spigot, and you can control how much you add. The goal, traffic engineering is pretty straightforward. The goal is to avoid getting above into this region. So you look at what's on the main line, and you look at what's left over, and you allow as much as what's left over in terms of how much flow you're allowing it. That's the simplest way to describe ramp metering. But what I just told you is that the way this is going to look is probably going to change. And so if you imagine that this collapses, now we might still be allowing this much in, but that puts us well into the congested region on a new fundamental diagram. Or, just as bad, we get those nice new fancy automated vehicles that grow that fundamental diagram. We're throttling ourselves with the current way we're doing it. So we really need to be responsive to who's there, because that who shows up to drive determines how that flow looks. So that's the main idea. To do this, we're going to use so we were talking about microscopic models. We're going to use a macroscopic model, which is basically a forced order partial differential equation that describes the flow of fluid. Specifically, we're going to use a discretization of this, which basically splits that road up into individual cells. We look at a discrete density in each cell and its average speed, and we can evolve that by looking at basically who flows from each cell into the next cell. It's called the cell transmission model. It's a commonly used sort of discrete solver for PDEs, and it works really well for our purposes. Okay, so we need to adapt that, though, for multiple classes of vehicles. The way I want to do this is basically track each vehicle independently, each class. However, the number of vehicles that can flow from one cell to the other is going to depend on not just how many vehicles of that class, so it doesn't just matter how many AVs or ACC vehicles are downstream, but it also depends on sort of how many other vehicles are in there. So there's a little bit of bookkeeping, a little bit of algebra we need to do, but we can update this sort of one class cell transmission model to a multi-class cell transmission model. If you're familiar with discrete solvers, this is probably not that tough of an exercise, but it's nice. And then we can run this ramp metering control. The ramp metering control I want to use is a simple feedback controller. It's called a linea. It's a simple linear feedback. You're basically going to look at, it's exactly what I described before. You're going to look at how many vehicles you let out before, and then you're going to look at the difference between your critical density, how many vehicles you could have on that road, and your current density, how many vehicles are currently there, and you're going to allow some fraction of that difference onto the road. So the lower the density on the main line, the bigger that difference is going to be, the more vehicles you'll let on from the ramp. I'm going to consider 3 different cases. So the first one is uncontrolled. This would be just free flow. The second one is what we're doing today. This is controlled, but we're going to assume a fixed fundamental diagram. So we're going to assume that that flow density relationship does not change with the percentage of automated vehicles. This is what we're doing today, right? And the third one is basically using our estimate of what those flow conditions ought to be by taking into account the fraction of vehicles that have different properties. What I want to show is just a simulation result and the results at the bottom. So we're looking at total delay. There's a couple other metrics you can look at as well, but we're going to look at total delay. That's sort of the difference between how long it would have taken a vehicle to traverse without the control versus with the control. Or sorry, if it were free flow versus with that current control. Uncontrolled, we see about 2.4 vehicle hours in this. I don't know, I think it's about 600-second simulation. No, it's a little longer. If we control with a static fundamental diagram, we're avoiding some of that congestion, but we're still basically pumping slightly too many vehicles into that road because we're not taking into consideration the fact that these ACC vehicles that are showing up to drive have different flow density properties. Whereas if we sort of dynamically update our controller, we reduce our total delay by about 25%. And so this is pretty nice. We're actually able to significantly reduce the total delay just by sort of updating our controllers to be more responsive to what's going on the roads. Okay, one sort of last quick aside here is I've talked about automated vehicles, but you could replace the word automated with aggressive vehicle for my entire talk, and I think everything would still be true. There's heterogeneity in how we drive. Every single one of us drives differently from others. In fact, I drive differently in the morning than I do in the afternoon, and I drive differently when I'm running late to something than when I'm not, right? And when we look at these macroscopic models, we sort of average all of that out, and we see a lot of scatter, and we're comfortable with it. But really, each vehicle is sort of locally affecting the dynamics of the flow. And if you're a really obstinate or a really bad driver, you are going to change the way things flow. And so you don't necessarily need this to be in response to automation. This could be in response to different types of drivers, different flavors of driving, et cetera. Okay, so the work that I've done here, I think it would be unfair to say it was me. A lot of this is obviously my students, so I have to acknowledge that both my former PhD students, Ming Feng, who's now at the University of Arizona, and Tianyi, who's at St. Louis University, as well as Amir, Shaga, and Ariane, and a number of undergraduate students have been involved with this, as well as external collaborators across the country and really around the world. One aspect that's been really fun about this work is people care about traffic. People care about traffic a lot. And so I've gotten to share a lot of this with local news outlets, Star Tribune, Care 11, et cetera. And it's been a lot of fun, sort of sharing some of the stuff we do here in the department with the broader public. Okay, so in summary, what did I talk about today? I think the key message is if you change the dynamics of a small number of vehicles, that changes the properties of the flow. That can be both good or bad, depending on how automation plays out. So in the short term, I think that might mean decreased capacity with partial automation, unless we all switch to electric vehicles. In the long term, it's likely that we'll see improved capacity. Either way, if you're managing the traffic, if you're managing transportation infrastructure, you ought to care, because this will change sort of what the capacity is of your roadway. What I outlined was a sort of a roadmap or an outline or framework for how we could use this information to slightly change our legacy infrastructure and hopefully sort of make that infrastructure future-proof, or at least more relevant into the future. I think we have a little bit of time for questions if there are any. Thank you very much for your attention.
Thank you so much, Raphael. I had one question, and it was related to model uncertainty.
Yeah.
So you have these models for your cars. I'm assuming they would different cars, different models, different tire pressure, different models. So I was curious how robust your results are to model error.
Yeah, that's a really good question. You mean like the big picture results at the end, or the like the microscopic vehicle models for like ACC vehicles, or all of the above? Yeah, that's a great question. Okay, so we do some like sensitivity analysis. Obviously, the downstream result of like expect to see a 35% decrease in capacity changes depending on what those models look like. I mean, what I've shown is kind of simplistic. We're assuming there's two types of vehicles. All humans drive one way, all automated vehicles drive another way. But what you can do is you can look at sort of calibrate models on a lot of different humans, for example. And we've done this. It's difficult because there's not that much data of this sort. We're trying to get access to that one data set that I showed at the beginning with like that really nice traffic jam in Nashville, because that would be like exactly what we need. But it turns out sort of when we do this with, I don't know, 30 different drivers, 25 different drivers, and we look at the variability, there is variability in those models, but generally that variability is smaller than sort of the downstream. So yes, that should be given with error bars that are maybe, let's say, 25 to 45 or something, but it's still an increase. Does that answer your question? Cool. Yeah.
Thanks for a really nice talk, Raphael. So I wondered how challenging it would be to extend these results, and I'm thinking particularly about the EV results, to financial implications. So if you think about balancing the idea that maybe we could jam more cars on the road and they would go faster if we all drove EVs, compared to the huge investments that we make in infrastructure, can a case be made for adding more rebates for EVs, kind of moving some of that money from infrastructure to EV?
Yeah,
That's
a really good question, because it gets at the heart of like what's important, and that is sort of like the budget on these things. So the results that I showed, sort of the most impressive results that I showed at the beginning, 5% makes an increase in like 5% vehicles drive differently, increase in like 15%. If you go up to like 80, 90%, you might see 20, 30% increase in capacity. And that's really nice. And then with EVs, right, we have, let's say, similar results because they drive better. If you take connectivity into account, you start saying, okay, if we can bring in connectivity, you get even better results. You see some estimates say maybe 2 to 3 times capacity. The thing is, like, we already have ways to do that. It's called bring a friend along, right? Like my car has 5 seats. It's normally just me, right? I could explode the capacity of a road if I just took people along. So yes, absolutely. You could, I haven't done that analysis of like, what are the financial implications and then what's the value of an individual EV from a capacity standpoint, because it saves us having to, if you drive with it, importantly with ACC turned on, if you don't drive with it with ACC turned on, I have no idea. I assume you're a great driver, Paige, but I have no idea how you impact the flow. But yeah, so you could make that, and I haven't done it. It's a good question. But I think that the bigger picture is like getting people to carpool is going to be an even cheaper approach if you can convince people to do it. But a good question.
This question is about lambda 2.
Yeah.
Your lambda 2s were all positive, and that seems to be the important parameter. And you would like them to be negative to reduce the magnitude of the waves that occur. Is it true, or I have this question, does a low positive lambda 2, is that better than a high positive lambda 2? Do you know that?
Yeah. It's a good question. It's a very good question. A low positive lambda 2 likely means that there's a lower range of frequencies of disturbance frequencies that are amplified. So sort of back of the envelope, yes. I have friends who are control theorists who would strangle me right now for saying that, because it's not quite that straightforward, but yes. And what you notice, if you look at the results, sort of exactly to that, there's 2 different, so for vehicle A, for example, there's 2 different A min and A max. A min is following at the closest spacing. So instead of following the 2-second rule, that driver is following the 1.4-second rule. And with the 1.4-second rule, you have a much bigger lambda 2 than when that same vehicle, so same engine, everything, drives at the maximum setting and is following the 2.8-second rule. And so, and generally, yeah, you see those disturbances propagate less or take longer to grow when you have a lower lambda 2. It's not quite that cut and dry, but generally speaking, yes. Keep in mind, though, from a capacity standpoint, it's not quite that obvious that the one vehicle is worse than the other, because if the vehicles are spaced twice as far, you now can fit half as many vehicles on the road at equilibrium. So it's not quite sort of a one-to-one correlation between being more string stable and necessarily being better for flow. Ideal for flow is only let one vehicle drive at a time, which is like obviously not optimal from a flow perspective, but it's good from a stability perspective.
Okay, I have a second part to the question.
Yeah.
If you take human drivers, what sort of lambda 2 value would they have? Would they have a positive? Is there any individual that has a negative lambda 2?
Yes.
It seems
Yes.
to be pretty
Yes.
hard to achieve.
Oh, yes. That one. So, okay. So again, I have to be careful here. I don't know if I have these in my appendix or not. I have to be careful here because there are, this is certainly not the case for everyone, or sorry, for all the time, right? But it's unlikely to be true for Paige, and I'll get to that in a second. So some drivers at certain times can be exhibiting string stable behavior. Some drivers might always be string stable. Truckers are generally the best. And that is because they sit slightly higher. And this is why, because I don't believe your car has a very high vantage point. If I recall, it has a relatively low vantage point. So if you're higher up, it's kind of cheating, but it's almost like connectivity. You have information about the flow that's further up, and you have information about what's going to hit you in a minute. And so it's almost like low-tech connectivity. And so what you'll see truckers do, and this is very common, there's this guy on YouTube who explains he calls it, what does he call it? He lives in the Seattle area, commutes, and he explains his philosophy about driving. And when I watch it, I'm like, you have summarized graduate level traffic flow theory in like a 2-minute YouTube video. And he films his commute and he explains how it makes maybe 1 second difference in terms of his arrival time, but he has no problem letting people cut in and sort of leaving a slightly larger spacing. or gap because he knows that that's going to then absorb these jams that will otherwise arise and amplify. And so truckers are the best at this because they have that higher vantage point and they can see when do they need to leave that extra spacing. And you'll see them do it because for truckers, braking is a like particularly high penalty because there's a lot of fuel needed to accelerate again. So they really would rather coast, and they see what the speed of that wave is, and they know that if they drive a little slower, they'll hit that wave right as it dissipates, and they'll be uninterrupted. So yeah, you absolutely can. And I urge everyone to do that. Drive a little less aggressively. Yeah, Ali Reza.
Okay. Thank you, Raphael. Great presentation. I really enjoyed. I have a question about that multi-class self-transmission model. That really interests me.
Okay.
I'd like to know what heterogeneity is captured among different classes. Like what characteristics of different classes are captured, like jam density, speed, and most importantly, whether overtaking is allowed in the model.
Yes, overtaking is allowed. Overtaking is allowed. That's fine. Actually, hold on a second. I'd have to double check on that, actually, on overtaking specifically. But basically what we're doing is we're assuming those models that we calibrated before. So we're using an IDM, an intelligent driver model, which is a very commonly used car following model for human drivers that lots of people have spent lots of time sort of finding the right model parameter values. And that's going to have both a different jam density, et cetera, but also just different, like the fundamental diagram for that model, if you take the microscopic model to the limit versus the model that we developed here, and then sort of take to the limit, it's going to be very different. So it's going to be a very not just different jam density, different capacity, different free flow, same free flow speed, different jam density, different capacity, because in free flow they're in free flow. But also sort of different curvature to that congested region of the fundamental diagram. So fundamentally different, again, fundamental, I shouldn't use it too much because of, but in principle, different models. I don't believe overtaking is allowed in that CTM, but I'd have to double check. I don't believe it is.
Thank you.
Yeah, thank you. Yeah, Tim.
I want to ask about roundabouts. So with the ACC, I'm going to kind of say this sarcastically. It seems like those are designed by my grandmother, who is super cautious, wants to make sure you don't get in an accident. And so it's actually, if I caught this correctly, and just a yes, no, they're worse than the average human.
Yes.
Okay. So
depends on what you're defining as worse, but yes, I want to be really careful here.
less optimal for traffic flow.
Yes, I think.
Okay. You talked about how the car companies won't talk to you. Will they listen to you? Is there any interest on the part of the car companies to actually improve traffic flow by listening to this type of research?
Yes. I would be disingenuous if I said no. They certainly, so I have worked with Ford before on something where they were trying to show something big demonstration. It was really cool. They brought me out to Michigan to this was right before I started here that summer. Brought me out to Michigan to their proving grounds, and they tested a bunch of different things. They are definitely interested. Early on, they were definitely interested. So they definitely took these things into account. If you look at the people who worked there early on and sort of the people they worked with, I'm glad you brought this up because it's something I didn't say, and that is that I don't blame the car companies. They are selling things that are safe. Talk to Professor Davis if you want more information on that, but are generally safe and that are comfortable, right? People want to use them. If they were, one way to be better would be to be more aggressive, right? But that would be very jerky and perhaps uncomfortable for the occupants. And so I think if you look at what they're trying to optimize, they're trying to make sure that they sell a product that's safe. All these systems are safe. And then they're trying to sell a system that people want to buy. The biggest complaint I will say that they're getting, and if you look at newer systems, they're better at this, is that they tend to leave too long of a headway. And so the number one reason, sort of anecdotally, when I talk to people and they say, oh, I don't like ACC because it leaves too big of a gap and people cut it in front of me. That's a valid criticism. Part of that is because, okay, I have a minute. Part of that is because of sort of what they're trying to do. They're trying to sell a really, really sophisticated automated vehicle without taking the sticker price up by maybe, I don't know, $1,000 or $2,000. And so if you look at someone like Tesla, well, let's look at someone like Waymo, right? Google's company that builds automated vehicles. Those things are several $100,000. And if you're trying to and a large part of that cost is you can't buy them to build. Large part of that cost is all the sensors, which have very low latency and are able to detect when the vehicle in front of you brakes very, very almost immediately. But that's obviously never going to work to put, I don't know, 150,000, even $20,000 worth of sensors on a car that you're trying to sell for 40,000 is just not going to work. And so car companies have generally bet on really low cost sensors like radar, which are, I don't know, a few dollars to install, but then have big latency because it's really sort of low quality signal. And so you have to do a lot of filtering to make sure that, yeah, that was in fact the car that was braking in front of me and not, I don't know, a pigeon that flew in front of me or something. And again, anecdotally, when I've driven these things, I've had people sort of merge from the lane to the right of me through to the lane to the left, and my car doesn't even react. And I'm guessing it's because it's still sort of filtering. It's looking at a point cloud in front of it, and it's still trying to decide, is that a car in front of me, or is that just a sensor error? Because you don't want it to be overreactive, because then it's going to start braking at things that aren't really there. And so I think the reason we have the systems we do, it's part of it's an artifact of they're trying to do a whole lot with a really low budget. And so as a result, they can't really afford to sort of put those high quality LiDAR sensors and things on these vehicles. If you look at Tesla, they've taken a totally different approach. So they said, instead of radar, I mean, they do have radar, their focus is cameras. Because they say if they put enough cameras are cheap. If they put enough cameras on the car and put enough sort of GPU or compute power in the car, they can get close to a LiDAR, that really high quality laser scanner, at a fraction of the cost. And they've been pretty successful with it. And so if you look at the way those vehicles drive, they do drive differently. And they are much less, I don't know your grandma, but much less like what I would imagine, what my grandmother drove like, right?
All right. Well, I think we've used our available time very wisely here. Let's give Raphael another hand.